A phylogenetic tree or evolutionary tree is a branching diagram or tree showing the inferred evolutionary relationships among various biological species or other entities, their phylogeny, based upon similarities and differences in their physical or genetic characteristics. The taxa joined together in the tree are implied to have descended from a common ancestor. Phylogenetic trees are central to the field of phylogenetics. In a rooted phylogenetic tree, each node with descendants represents the inferred most recent common ancestor of the descendants, and the edge lengths in some trees may be interpreted as time estimates. Each node is called a taxonomic unit. Internal nodes are generally called hypothetical taxonomic units, as they cannot be directly observed. Trees are useful in fields of biology such as bioinformatics, systematics, and phylogenetic comparative methods. Unrooted trees illustrate only the relatedness of the leaf nodes and do not require the ancestral root to be known or inferred. History. The idea of a tree of life arose from ancient notions of a ladder-like progression from lower to higher forms of life. Early representations of branching phylogenetic trees include a paleontological chart showing the geological relationships among plants and animals in the book Elementary Geology by Edward Hitchcock. Charles Darwin also produced one of the first illustrations and crucially popularized the notion of an evolutionary tree in his seminal book The Origin of Species. Over a century later, evolutionary biologists still use tree diagrams to depict evolution because such diagrams effectively convey the concept that speciation occurs through the adaptive and semi-random splitting of lineages. Over time, species classification has become less static and more dynamic. Types. Rooted tree. A rooted phylogenetic tree is a directed tree with a unique node corresponding to the most recent common ancestor of all the entities at the leaves of the tree. The most common method for rooting trees is the use of an uncontroversial outgroup close enough to allow inference from trait data or molecular sequencing, but far enough to be a clear outgroup. Unrooted tree. Unrooted trees illustrate the relatedness of the leaf nodes without making assumptions about ancestry. They do not require the ancestral root to be known or inferred. Unrooted trees can always be generated from rooted ones by simply omitting the root. By contrast, inferring the root of an unrooted tree requires some means of identifying ancestry. This is normally done by including an outgroup in the input data so that the root is necessarily between the outgroup and the rest of the taxa in the tree, or by introducing additional assumptions about the relative rates of evolution on each branch, such as an application of the molecular clock hypothesis. Bifurcating tree. Both rooted and unrooted phylogenetic trees can be either bifurcating or multificating, and either labeled or unlabeled. A rooted bifurcating tree has exactly two descendants arising from each interior node, and an unrooted bifurcating tree takes the form of an unrooted binary tree, a free tree with exactly three neighbors at each internal node. In contrast, a rooted multificating tree may have more than two children at some nodes, and an unrooted multificating tree may have more than three neighbors at some nodes. A labeled tree has specific values assigned to its leaves, while an unlabeled tree, sometimes called a tree shape, defines a topology only. The number of possible trees for a given number of leaf nodes depends on the specific type of tree, but there are always more multificating than bifurcating trees, more labeled than unlabeled trees, and more rooted than unrooted trees. The last distinction is the most biologically relevant. It arises because there are many places on an unrooted tree to put the root. For labeled bifurcating trees, there are total rooted trees and total unrooted trees, where represents the number of leaf nodes. Among labeled bifurcating trees, the number of unrooted trees with leaves is equal to the number of rooted trees with leaves. Special tree types. A dendrogram is a broad term for the diagrammatic representation of a phylogenetic tree. A cladogram is a phylogenetic tree formed using cladistic methods. This type of tree only represents a branching pattern, i.e., its branch spans do not represent time or relative amount of character change. A phylogram is a phylogenetic tree that has branch spans proportional to the amount of character change. A chronogram is a phylogenetic tree that explicitly represents evolutionary time through its branch spans. A spindle diagram is the representation of the evolution and abundance of the various taxa through time. A dalgrenogram is a diagram representing a cross-section of a phylogenetic tree. A phylogenetic network is not strictly speaking a tree, but rather a more general graph or a directed acyclic graph in the case of rooted networks. They are used to overcome some of the limitations inherent to trees. Construction. Phylogenetic trees composed with a non-trivial number of input sequences are constructed using computational phylogenetics methods. Distance matrix methods such as neighbor joining or UPGMA, which calculate genetic distance from multiple sequence alignments, is simplest to implement, but do not invoke an evolutionary model. Many sequence alignment methods such as cluster also create trees by using the simpler algorithms of tree construction. Maximum parsimony is another simple method of estimating phylogenetic trees, but implies an implicit model of evolution. More advanced methods use the optimality criterion of maximum likelihood, often within a Bayesian framework, and apply an explicit model of evolution to phylogenetic tree estimation. Identifying the optimal tree using many of these techniques is NP-hard. So heuristic search and optimization methods are used in combination with tree scoring functions to identify a reasonably good tree that fits the data. Tree building methods can be assessed on the basis of several criteria: efficiency, power, consistency, robustness, falsifiability. Tree building techniques have also gained the attention of mathematicians. Trees can also be built using T-theory. Limitations. Although phylogenetic trees produced on the basis of sequence genes or genomic data in different species can provide evolutionary insight, they have important limitations. Most importantly, they do not necessarily accurately represent the evolutionary history of the included taxa. In fact, they are literally scientific hypotheses, subject to falsification by further study. The data on which they are based is noisy. The analysis can be confounded by genetic recombination, horizontal gene transfer, hybridization between species that were not nearest neighbors on the tree before hybridization takes place, convergent evolution, and conserved sequences. Also, there are problems in basing the analysis on a single type of character, such as a single gene or protein, or only on morphological analysis, because such trees constructed from another unrelated data source often differ from the first, and therefore great care is needed in inferring phylogenetic relationships among species. This is most true of genetic material that is subject to lateral gene transfer and recombination, where different haplotype blocks can have different histories. In general, the output tree of a phylogenetic analysis is an estimate of the character's phylogeny and not the phylogeny of the taxa from which these characters were sampled, though ideally, both should be very close. For this reason, serious phylogenetic studies generally use a combination of genes that come from different genomic sources, or genes that would be expected to evolve under different selective regimes, so that homoplasy would be unlikely to result from natural selection. When extinct species are included in a tree, they are terminal nodes, as it is unlikely that they are direct ancestors of any extant species. Skepticism might be applied when extinct species are included in trees that are wholly or partly based on DNA sequence data, because little useful, ancient DNA is preserved for longer than 100,000 years. and except in the most unusual circumstances, no DNA sequences long enough for use in phylogenetic analyses have yet been recovered from material over 1 million years old. The range of useful DNA materials has expanded with advances in extraction and sequencing technologies. Development of technologies able to infer sequences from smaller fragments, or from spatial patterns of DNA degradation products, would further expand the range of DNA considered useful. In some organisms, endosymbionts have an independent genetic history from the host. Phylogenetic networks are used when bifurcating trees are not suitable, due to these complications which suggest a more reticulate evolutionary history of the organisms sampled.